Our next sample problem here kind of walks through Lewis structures for octet rule exceptions. Again, this is the 5th sample problem, so I'm going to assume we're pretty proficient with writing our Lewis structures. So I'm going to go fairly quickly here. So our first example here is SClF5. Again, figuring out how many electrons we have. We've got 6 electrons for our sulfur, plus 7 electrons for the chlorine, plus 5 of the fluorines gives us another 35 electrons. So we've got 48 electrons total. Put our sulfur in the middle, okay? And we're going to have chlorine and then 5 fluorines. 2, 4, 6, 8, 10. 2, 4, 6, 8, 10, 12 electrons we need to take away from gluing everything together with single bonds. Gives us 36 electrons remaining. And again, I can already see there's 1, 2, 3, 4, 5, 6 halogens around there. Each of them likes to have 3 lone pairs, 6 electrons total. So those 36 electrons are going to fill up the rest of my octets. So I'm not going to count while I do these. So complete octet for all of our halogens, but we can see that sulfur actually has 12 electrons around it. So in terms of the octet rule exception, this is an expanded octet. And this is okay when you are an atom that's in row 3 or below on the periodic table. We can't do that for oxygen. And again, a lot of the atoms that you'll encounter when you go on and take organic chemistry are things like carbon, nitrogen, oxygen, hydrogen. These are not octet violating atoms. So you're never going to have more than 4 bonds or more than 8 electrons around these atoms. But get down on this 3rd row of the periodic table and below, absolutely. So things like phosphorus and sulfur are going to expand their octets. And that's okay. So that's the structure for SClF5. I'm going to go ahead and do C first because B is going to be one where we've got 2 resonance structures to draw, and then we'll be able to select the most important. Okay, so BFCl2. So boron is going to give us 3 electrons. We've got 7 from our halogen as fluorine, and then another 14 electrons from the 2 chlorines. So that gives us 18 electrons total. Remember, halogens like to be terminal peripheral pieces. So I know that boron's going to be my central atom, and I'm going to have my fluorine, chlorine, and my other chlorine here. So that's going to take up 6 electrons. Okay, do my subtraction. And I'm left with 12 electrons that oops, it's 24 electrons. Math was off there, sorry. So I have 24 electrons total. Now once I subtract my 6 electrons, I'm left with 18. Each of these is going to want 6 as lone pairs. So that's going to take up my 18, right? 2, 4, 6, 8, 10, 12, 14, 16, 18. Now, it looks like we've got a problem because it looks like boron has an incomplete octet. And indeed it does. So boron has an incomplete octet. But that, again, is okay because when you're from group 2 or group 3, you don't want a complete octet because that would give you a formal charge that's undesirable. Remember where boron is in the periodic table. It only has 3 valence electrons, so it only wants 3 electrons around it. So it wants 3 electrons. When it bonds 3 times with no lone pairs, that gives it a formal charge of 0. So that's a desirable situation. All right, so that's the C problem. So let's spend a little bit more time now on our B problem and look at how to draw phosphoric acid, H3PO4. And this is again where I'm going to kind of draw on you to think about some of those rules we talked about earlier in terms of how do things like to bond. Remember in sample problem 10.2, we kind of looked at how do things like to bond. And I'm going to use this when I'm going to piece together H3PO4. Okay, so let's just talk about the glue that we have here. 3 hydrogens, 3 electrons. A phosphorus is 5 electrons, and then 24 electrons for our 4 oxygen atoms. So that gives us 32 electrons to build this molecule. All right, phosphorus I know is going to be a central atom, okay? And I've got 4 oxygens, and I know that my hydrogens like to be peripheral. So I'm going to space things like this to start. I'm going to put hydrogens around the end here, and we'll see where this leaves us. 2, 4, 6, 8, 10, 12, 14 electrons that I used up to glue everything together with single bonds means that there's 18 electrons left over. 2, 4, 6, 8, 10, 12, 14, 16, 18. All right, used up all my glue there. Let's figure out formal charges. 0, 0, 0, right? Remember, every time we see something bonding like we want it to, oxygen likes to bond with 2 bonds and 2 lone pairs. That'll give it a 0 formal charge. All right, but this oxygen atom owns 7, wants 6, formal charge of -1. Now wait a minute. This molecule didn't have an overall charge, so there must be someone somewhere that has a +1 formal charge. Let's check out phosphorus. Phosphorus wants 5, right, based on where it is in the periodic table, wants 5. It only owns 4 here. So there's where my +1 formal charge comes from. Okay, remember, sometimes we said if you have adjacent formal charges that are opposite in their charge, somebody might have a pair when they're supposed to share. So let's try moving these electrons down as a bond. Now with phosphorus, we can do that. We can have phosphorus have more than 8 electrons around it. So I'm going to draw this again as a resonance structure. As a double bond here. Everybody else stays exactly the same, but let's see what this does. Now this oxygen atom has a formal charge of 0, and now this phosphorus, and having 5 bonds around it, means it owns the 5 electrons that it wants to own. So now my phosphorus also has a formal charge of 0. Well, that's really good because I've drawn a Lewis structure here where nobody has formal charges. That's desirable over a Lewis structure where there are formal charges. So this is my preferred Lewis structure and the best resonance structure for this molecule.